All right, so 13.3 part 2. Higher order.
That's a darn shame.
Higher order partial derivatives. Okay, so just like with single variable functions, we can extend our idea of partial derivatives and talk about higher order partial derivatives, second partial derivatives. And like we mentioned the other day, because we have two variables, we get more kinds of second partial derivatives. So we're going to say we have z equals some function of x and y. So for a second partial, derivatives, normally we say second partial. We have four possibilities. So our first possibility is we can take the derivative. If we take the first derivative with respect to x, we can take the second derivative with respect to x. And the way we write that is f sub xx, or d dx of df dx. And the shorthand way we write this is d squared f dx squared. So that's our first possibility. Our second possibility, we could take our first partial with respect to x and our second partial with respect to y. And we write that as f sub x y, and that's the partial with respect to y of df dx. And we write that d squared f dy dx. So first thing to notice here is on this mixed partial, when we use the subscript notation, the order in which we do our derivatives is from left to right. We do the partial with respect to x and then the partial with respect to y. When we use the d notation, our order of derivatives is from right to left. We take the derivative with respect to x and then the derivative with respect to y. So the orders are reversed. So you need to be aware of that difference. So those are our first two possibilities. The next two come from starting with the partial with respect to y. So we say f sub y. We can take the partial of that with respect to y. So that's f sub y. Just writing down all the ways we notate this. So that's our partial with second partial with respect to y, and then we can form our what we call our mixed partial. F sub y first, partial with respect to y, and then we differentiate that with respect to x. And that's a partial with respect to x of df dy. And we write that d squared f dx dy. So again, it's important to keep the subscript notation. Remember how the subscript notation works. When we use the subscripts, our order of the derivatives is from left to right. When we use the d notation, it's from right to left. And with the d notation, if you think of this intermediate step, if you can't remember that intermediate, thinking of that intermediate step can help you remember how that works. So our second option and our fourth option, we call the mixed partials. So those would be our mixed partials. And the mixed partials turn out to be there's some interesting things that happen with the mixed partials. So this is how we define our higher order partial derivatives. Nothing different, nothing unusual really. Just because we have more than one variable, we have these various possibilities. In advanced calculus, we can prove that if the mixed partials are continuous, if our mixed partials are continuous, then they are equal. So that's the first interesting thing that happens with the mixed partial. So we're usually going to be working with nice functions that are going to have continuous second partial derivatives. So for the most part, that's what we're going to be looking at. Things get more complicated if you're looking at functions that behave differently. For the most part, we're going to be working with functions that have continuous mixed partials. So we're going to say, for what we're doing, that for some function of x and y, and the technical way we say it is these are our mixed partials are continuous on an open disk. Open disk, radius r. Then our mixed partials, f of xy equals f of yx for every point in the disk. So what we're saying here is as long as in some area of the plane our second partials are continuous, then our second partials are going to be equal in that disk in the plane. So if our disk is really large, then our function is really nice. If there's just some small place where they're continuous, then we can say our mixed partials are continuous in that little place. For the most part, we're going to be working with functions where our mixed partials are equal everywhere, for the most part. And this idea holds for functions of 3 or more variables. So for a 3-variable function, if the second partials are continuous, then the third mixed partials would be equal. If the third partials are continuous, then the fourth mixed partials are going to be equal. So we can extend this idea as far as we want. Same conditions are holding for functions with more than 2 variables. So what I want to do, today I just want to introduce the idea of the second partials. I just want to do some examples working with our second partials, and then we'll ask some questions that have to do with second partial derivatives. And then I want to talk really briefly at the end about the idea of differentiability of a multivariable function. So before we go on, any questions on what we mean by second partials? And this property is going to come in handy in several different places when we talk about our second mixed partials being equal. All right, so let's look at this function. z equals x to the fourth minus 3x squared y squared plus y to the fourth. We want to find the four mixed, or so we want to find the four second partials. So to find our second partials, we have to start by finding our first partials. So let's find our first partials, dz dx. So what's dz dx going to be for this function? 4x cubed minus 6x y squared. And our y to the fourth is constant, so that's all we have. And then our dz partial with respect to y, dz dy. So what do I get for dz dy? Minus 6 x squared y plus 4y cubed. Now we're going to find d dx of dz dx. We're going to take the derivative of this with respect to x. So what do we get when we take the derivative of this with respect to x? Got to start at 12 x squared minus 6 y squared. And let's do the partial of this with respect to y. So when we take the partial of this with respect to y, we get minus 6x squared plus 12y squared. And then we'll take the partial, our mixed partials. What's that?
Oh, are you thinking of the one on top?
Yes, the one on top. Yeah, so I'm just going to do them in columns here. So I'm doing the partial with respect to y of this thing. All right, and then the partial with respect to y of dz dx. Partial with respect to y of this thing, and I get minus 12xy. Partial with respect to x of this thing, dz dy, and I get minus minus 12 xy. And our second mixed partials, we see that our second mixed partials are equal. Questions there? All right, let's look at a three variable function. And let's say we have f of xyz is x squared plus 3xy plus 4yz plus z cubed. And we want to show, this asks us to show that f of x y equals f sub yxy, and that equals f of yx. We want to show that all three of those are equal. So we're going to start for this first one. Let's take the partial with respect to x. So the first partial with respect to x of this thing is going to be 2x. And let's see, this should be a minus. I want this to be minus. 2x minus 3y. And then let's do that with, let's do f sub xy. So this time I'm going across here, f sub xy. I get minus 3, and then f sub xyy. Partial of this with respect to y is 0. Now let's do our partial with respect to y here. So starting on the second one, partial with respect to y is minus 3x plus 4z. Take the partial of that with respect to x, f sub yx is minus 3. And finally, for the last one, f sub y x y is 0. And I already have the partial with respect to y here. So I'm going to take the partial of that with respect to y. F sub yy is 0. So this last one's easy. F sub yx is going to be 0. So these third mixed partials are all equal for this particular function. All right, questions on the process of taking second partial derivatives? Nothing really different than what we've done before. We just have to keep track of our variables, and depending on how the problem's given, we need to keep track of our subscripts in the order that we're doing our partial derivatives. All right, now I have a couple of questions about partial derivatives for you guys. So for this one, we're going to say that n equals the number of applicants to a university. And what's that?
This might become really depressing.
And that P is the cost of food and housing.
Also very depressing.
Yeah, and that never changes. The part about cost of food and housing being depressing. And T equals the cost of tuition. So we're going to say for this, we're going to consider n is a function of P and T. So somehow the number of applicants depends on these things. And this function behaves such that the partial of n with respect to P is less than 0, and the partial of n with respect to T is less than 0. And I want to know, what does this tell us? So we have this function and we have these partial derivatives that are less than 0. So what does that tell us? How do we interpret these results? So Max says the maximum number of applicants is when you don't have to pay.
I would never guess.
So let's make our interpretation a little more broad. What does this tell us about this? What does this tell us about the applicants and the food and the tuition and how those are all related?
As the cost goes up, the number of applicants goes down.
As the cost goes up, the number of applicants goes down, and either of the costs, right? As the tuition goes up, the number of applicants go down, and as the cost of food and housing goes up, the number of applicants goes down. So our number of applicants decreases as our cost increases. Make sense? All right, these next ones are true or false. I love these true or false questions. And we want to explain. So my first one, number one, I'm going to say if z is a function of two variables, and the partial of z with respect to x equals the partial of z with respect to y, then z is some constant times x plus y. If the first partial with respect to x equals the first partial with respect to y, then z has to be some function that looks like a constant times x plus y. Is this true or false? And we want to explain.
False.
Max says false.
It could be just a constant.
Okay, so Max says z equals a constant. The derivative of this constant with respect to x is 0. The derivative of the constant with respect to y is 0, so they're equal. But this function is not in that form. So that's a nice, easy counterexample. Anybody think of any other types of counterexamples? Any other types of functions where the partial with respect to x and the partial with respect to y are equal, but the function doesn't look like this? I'm going to think of another really easy one. Okay. Max says z equals e to the x plus y. The derivative partial with respect to x of e to the x plus y is just e to the x plus y. Partial with respect to y is e to the x plus y, and they're equal. I also thought of would z equals a natural log x plus y work? Yeah? The easy one I was thinking of is z equals, how about z equals x plus y plus 1? So our second partial, or our first partials with respect to x and y would be equal, but our function is not in that form. So those are some examples of functions. Z equals xy. First partial with respect to x is y. First partial of y is x. So that one doesn't work. So those are some counterexamples to this claim. Let's see. Next one, true or false? Did we decide we like these true or false questions? These would be good test questions? No?
True or false?
If they're the exact
Yeah,
same
no,
question.
yeah.
They're these,
Yes.
These,
Yeah,
yeah.
they're not different.
These,
Then
different.
no.
They are-
Yeah.
they are good.
That's like the,
We should just make the test. Yeah, I can do that. Yeah.
There's the joke about the students that ask if the test, what the questions on the test, the final are going to be like, and the professor says, Well, they're going to be like the other questions we had, but the numbers will be different. But then the professor says, well, pi will be the same, e will be the same. So not all the numbers will be different. Anyway, so if z equals f of x times g of y. So f is a single variable function, g is a single variable function. Then dz dx plus dz dy equals f prime of x times g of y plus f of x times g prime of y. So if my function z, my two variable function can be broken up as a function of x times a function of y, then our sum of our first partials is this thing. We want to know true or false and explain. So what can we do to figure this one out? Could we just take our derivatives? Find our derivatives, our partial derivatives? So for this particular function, what is going to be dz dx? Partial with respect to x. For this function. G of y is just a function of y, so what do we consider that one? A constant. And what's the partial? So we have a constant times f of x. How do we take the derivative of that? Isn't it just f prime of x times our constant? And then dz dy, the partial with respect to y. F of x is a constant, so that's just going to be our constant times g prime of y. And when we add them together, we get this. So that is true. And this our project that we'll do this semester, this true or false question kind of reminds me a little bit of our project. All right. Last true or false question. So this one really is just, you just need to find the answer. If z equals e to the xy, then d squared z dy dx equals xy plus 1 e to the xy. So this one you just need to find the answer. So do the second mixed partial and tell me if this is true or false. Anybody got it? What do you think, Robert? Robert says true. So when you calculated, so we need to calculate the partial with respect to x first, right? So dz dx, the partial with respect to x. What did you get for that, Robert? Y e to the xy. And then we're going to take the partial with respect to y of that, so dy of y e to the xy. We have to use the product rule, right? So when we do the product rule, we get y x e to the xy plus e to the xy. Factor out the e to the xy, and we get xy plus 1 e to the xy. So that is true. So that was an easy one. Could put that one would be okay to put on the test. All right, questions on those examples? All right, last thing I want to talk about is just kind of a little, not exactly a preview for Friday, but to kind of to introduce in a kind of a roundabout way what we'll talk about tomorrow. Tomorrow we're going to talk about differentials. But differentials for multivariable functions have to do with differentiability. So for a single variable function, we define differentiability by saying that we said that a function is differentiable if the derivative exists at a point. Well, for multivariable functions, it's a little more complicated, because our derivative can exist at a point where a function is not continuous. So we need a little different definition of differentiability. So for a single variable function, we said the function is differentiable if the derivative exists. And we said there was a connection between differentiability and continuity. There is a connection between differentiability and continuity for multivariable functions, but the idea of differentiability is a little different, because we can have the derivative exist at a point of a multivariable function where the function is not continuous. So I wanted to look at an example of that. So let's say we have f of xy, and we're going to define this as a piecewise function. We're going to say this function is 0 for xy not equal to 0, and it's 1 for xy equal to 0. First thing I want to do is make a little sketch over here. I'll get an idea of what this function looks like. And I'm going to put my axis over this way, like so. So there's my coordinate system. Z, Y, and X. So we're going to have a surface. So our surface is, our Z value is 0 everywhere that XY is not equal to 0. Well, where in space is xy not equal to 0? Along x equals 0 and along y equals 0, the product of x and y would be 0, right? Along x equals 0 or along y equals 0, the product would be 0. So our surface is at a z value of 1 where x equals 0 and y equals 0. Where is x equals 0 and y equals 0? Where are those things? Where is x equal to 0? Along the y-axis, right? So So along the y-axis, I'm going to be 1 unit above the xy plane. So let me draw that in. And I'm going to make my line kind of thick here. So we're going to be 1 unit, and I'll put it like so. 1 unit above the xy plane. My surface, when x, that's when y equals 0. So there's my surface in that case. We get a line. And where's y equals 0? Or sorry, so this is x equals 0, so where's y equals 0? Along the x-axis. So I get a surface, part of my surface is up above here, 1 unit above the x-axis. And I'll go back this way. So when y equals 0, I get these lines 1 unit above the xy plane. Where is xy not equal to 0? The product not equal to 0. Isn't it anywhere else in the xy plane except the x-axis and the y-axis? Anywhere in here, my product is not going to be 0. So I'm going to do that. I'm going to shade that in red. So I get in the xy plane, I get my surface is basically the xy plane everywhere except the x and y axis. So this entire xy plane except the xy axis. So there's my surface. In the xy plane that's here, along the x and y axis, I get these lines 1 unit above the xy plane. Now let's look at the point here. Let's look at 0, 0. We want to look at the limit as xy approaches 0, 0 of that. So we want to find that limit. We're going to look along 2 different paths. So we decided that our function would not be continuous if our limit wasn't the same along two different paths. So let's look along y equals x. So we're on a line here in the xy plane. We're looking along this line in the xy plane, y equals x. Well, in the xy plane, no matter where we are, what is my function value? 0, and no matter where I am along this point, my limit, that I'm going to be very, very close to 0 because my function value is 0. Along y equals x, the limit equals 0. How about along y equals 0? So along the x-axis. What is my limit going to be along the x-axis? No matter where I go, from the left, from the right, my function is 1. Along y equals 0, the limit is 1. So our function is not continuous at 0, 0. And now let's think about df dx, our partial with respect to x, and our partial with respect to y. What is the slope? What is the slope of this? We think of the partial as the slope of the surface, a curve on the surface. So what is the slope of the curve along the line x equals 0? What's the slope? 0. What's the slope along the line x equals 0, along the y-axis? 0. What's the slope down here on the xy plane? 0. At 0, 0, both of these partial derivatives and df dy exist and equal 0. So we have, at a point where a function is not continuous, we have derivatives that exist. So this is an example of why we have to do something a little different to define differentiability, because we can have a function that's differentiable at a point where our function is not even continuous. So our ideas of differentiability have to be a little bit different. We'll talk about how we define differentiability for a multivariable function tomorrow when we talk about differentials. So we can't say that a multivariable function is differentiable because the derivative exists. Because here we have the derivative existing at a point where our function isn't even continuous. So things are a little more complicated for multivariable functions. And we'll talk more about that tomorrow. All right, questions? So the point of this, I guess I'll say differentiability is more complicated for multivariable functions. All right, homework. So this is another place where the derivatives are the same, except they're kind of a little bit different. Page 896. There you go.